We're now going to complete an ANOVA test. You are a market researcher and you want to know if there is a difference in the way people perceive the quality of coffee between the major brands. You suspect that all brands share the same mean satisfaction for the coffee's taste, but you are not sure. You give people a customer satisfaction survey and ask them to rate the coffees on different factors and get a score out of 100. Use significance level of 0.05. So here we have different customers satisfied. Tom Honey's has 4, Third Mug and Jack Daniels have 6, and Moon Dollars has 5. When you complete an ANOVA test, we make 3 assumptions that must be true. The first is that populations have a normal distribution. The second is that the population standard deviations are equal. And third, that populations are independent. So these aren't the same customers trying all the different coffee and then giving their results. That would be paired or dependent samples. So the textbook outlines, your textbook outlines 5 steps, and we'll follow these now. First, we need to state the null hypothesis and the alternative hypothesis. Now we assume that the standard deviations are all the same, and we can also, our null hypothesis is that all the treatment means are equal. Now, sorry, when I say treatment, we have 4 different sets of samples, and we call them treatments. We have 4 treatments. So if you're testing to see if all the treatment means are equal, so our null hypothesis is that the mean of 1 equals the mean of 2, which equals the mean 3, which equals the mean of 4. Our alternative hypothesis simply states that the mean scores are not equal. Now, we can also think of this as saying that at least 2 mean scores are not equal. 3 of these may be the same equal, but if one of them is not, then they are non-equal. If the null hypothesis is not rejected, we would conclude that there is no difference in the mean for the satisfaction ratings of the 4 coffee companies. If our null hypothesis, this should say, have those backwards. If our null hypothesis is rejected, we would conclude that there is a difference of at least 1 pair of mean scores, although we won't be able to at this point say which pair or how many differ. So step 1, setting up our hypothesis. Step 2, we need to set our significance level. Now we have had that set for us, but it is important to take note. So we have a significance level of 0.05. Step 3, is we need to determine the test statistic. So now our test statistic will be what we would find in the F distribution table. The F distribution table will tell us when we reach that 95% confidence. So what we do is we kind of set the marker of where 95% is. If we go over the 95% or vice versa, less than 5% significance, then we know we can reject the null hypothesis. But if our samples show that this is a normal distribution of our samples, and that we could have, let's say we can expect to see something like this half the time, or 40%, or even 6% of the time, then we can't reject it. Now, remember, when we test hypothesis, we're not saying in absolutes. We can never say that it is true or false. We're just that we can't. There's not enough evidence to reject it. So let's do that let's test the statistic for the F distribution. Sorry, the test statistic will be F distribution, and step 4 is to determine the decision rule. So the decision rule is what number of our F distribution will we need to find where we have an acceptable answer, that we can reject our null hypothesis or confirm it. So when we look at our F distribution tables, you can see that we have a numerator of degrees of freedom and a denominator degrees of freedom. So what we need to do is determine our degrees of freedom. You can find this on your formula sheet, but you'll be able to, the numerator degree of freedom is k minus 1, whereas k equals number of treatments. So in this case, we have 4 samples, which, remember, we call treatments when we use the ANOVA. So our numerator degree of freedom would be 4 minus 1, which equals 3. So that's our numerator degree of freedom. Our denominator degree of freedom is n minus k. So whereas n equals the number of observations and so we can count up our number of observations. We have 4, plus 6 is 10, plus 6 is 16, plus 5 is 21, and k remains our number of treatments. So we have 21 less 4, which equals 17. So we've now set our decision, the degree of freedom on our numerator of 3 and a degree of freedom for our denominator of 17. We're using our F distribution table. We've set our significance level at 0.05. So now we need to go to the F table for 0.05. So it's very important that you find our F distribution at 0.05. Right here we can see our numerator degree of freedom is 3, so we'll move here. Our denominator is at 17, and we get a 3.2 F value. So if our F value exceeds 3.2, we will reject the null hypothesis. In layman's terms, if our F value is higher than 3.2, the probability of getting this specific set of samples is so low, well, it would be under 5% because we've set our significance level at 5. So the probability that we could get this specific set of samples would be set to 5%, would be less than 5% if the F value that we are about to compute is higher than 3.2. If it's lower than 3.2, we would have a probability of more than 5%. So we could get this specific set of samples more than 1 in 20 times, or something similar. And so we would not have the evidence to reject our null hypothesis. Now we need to calculate our F value. And this starts us up on our final step. So our step 5 is to select the sample, perform the calculations, and make a decision. A convenient way to summarize our calculations of the F statistic is in what's called an ANOVA table. The format of ANOVA is as follows. We have our source of variation, our sum of squares, our degrees of freedom, our mean square, and finally our F. Our source of variation will come from our treatments and our error. We'll then have our totals, and we will enter our calculation numbers here. So we'll follow these steps to finally get our F value. So we're going to start by finding our finding our SS and our SSE, then finding our SST by subtraction. So we start by finding here, and then we would find our SSE, and then we can subtract this amount from this amount to find our SST. So to do that, what we need to do is finding our SS. Now our SS total, which is our which means our total variation, so our SS would be our total variation, can be found using the following formula. Again, we're looking for this. Where X is our simple observation, and our X bar is the overall or grand mean. So all of the observations in all the treatments are overall mean. So to do that, what we need to do is determine our grand mean, and we need to find the individual amount for each of these observations. So we can use the space in between this to determine that. We'll start by totaling up all of these observations. So our total and the total of all four would be 1600. Now we can find the mean of each one. We'll put the mean above them here. So the mean, for each one we have 4 observations and 337 total. So we would get a mean of 84.25. 6 observations and 485 total. 80.33. Pardon me, 80.83. 406 and 6 observations. 67.67. And 372 and 5 observations, we have a mean of 74.40. And we have all of the observations 21 and all of the totals 1600. So we would get a grand mean of 7619. Now our SS total formula shows that we actually need to get our simple observation, so each one of these observations less the grand mean, and then we'll square them. We'll add them up and we'll square them. So again, just to be clear, this is not going to be 81 less 84.25, because this is not the treatment mean. This is the grand mean. Here we have our simple observation. So we're going to use our grand mean total of 7619. So it would be 81 less 7619. I'm going to leave some room because we will need to square these to get the variance. So again, 89 less 7619. And so we've determined our simple observation less our overall grand mean for each observation. And now we need to add up. So we need to square each of these numbers because, as you can see here, these are in brackets, so we square it and then we add them all up to get our SS total. So once again, I'm going to square them right beside it. If you feel the need to create a new chart, feel free to do so. This might get a little tight. This is an example where it's very nice to use Excel. Okay, so this is very tight, but again, we're going to add up all these categories to get our SS total, because as you can see, the formula has us adding them up after we square them. And we get our SS total, which again means our total variation. And the total comes to 2163.24. So our SS total is 2163.24. So I know the ANOVA table can seem very overwhelming. It doesn't need to be if you follow the steps. It's just a little time consuming. So now we can find our SSE. Now this is our variation within our treatments. Our SSE total is the sum of our observation, that's our X bar, which is our sample mean for the treatment, squared. So in this case, our X is the observation, simple observation, and XC is the sample mean from that treatment or that column. Now, do you remember how when we did the SS total, we used the grand mean? Well, now we're using the column mean. So what we can do, what we would do, or what we will do, is we'll use our individual mean. So this would be A, this would B, C, D. And we would less 81 from X bar A, 89 from X bar A, and so forth. Now I've ran out of room on this table, so we can do it simply by hand, and I'll get us started just so you can see, which equals 81 less 84.25 squared plus 89 So do you see how I'm using our column mean, our treatment mean, not our grand mean, but our treatment mean. So as we move along here, we would take our simple observations and less the amount. Now they are going to be squared. I'm not going to do that for time's sake. We're already over 30 minutes on this video. But you will do that for each one. If you want to build another table, that's totally reasonable. If you just want to do it by hand and take this and so we would take 81 less 84.25, the negative 3.25, and we square it, and we get 10.5625 plus here our second observation, right? Our second observation, 89 less 84.25, 4.75, we square it, 22.5625 plus, and we would do that for all of our observations here. And again, we're going to switch to whichever treatment mean we get. Again, I'm not going to do that for simplicity. I think you know how to do that basic math. We're going to get a total of SSE total of 1,322.12. So we can enter that here into our ANOVA chart. So if we know our total and we know our SSE, which is which means our variation, our means variation within the treatments, we can determine our SST, which means the variation due to different treatments. That will equal 841.12. So we can now use these to determine our F value. So we're going to continue along our table. We've already determined our degrees of freedom. So our K minus 1 is 3. Our N minus K is 17. And we can determine our mean square. So our SST here divided by our K minus 1, or our degree of freedom, 3, brings us a total of 280.37. Now our MST is our mean square of our treatment, and our MSE is our mean square of our error. So again here, we can take this amount, divide it by our degree of freedom, and we would get 1322.12 divided by 17 is 77.77. And just like that, we have our two mean squares. So again, I know the ANOVA table can seem very overwhelming. It seems like it's a lot, and it is a fair amount of work. There's nothing here that isn't too insanely difficult. It's just a lot of organization. This is why we create the table, and we follow our 5 steps to make it very clear. So now we can take our MST, or our mean squared of our treatments, and divide it by our mean square of our errors. And that's going to determine our F value. So 280.37 divided by 77.7. We get a F amount of 3.61. So let's have a look at the steps that we took at the beginning. We've set our significance level. We're using F distribution, and we used our degrees of freedom to determine our decision rule. We found that the F value, the critical value, is 3.20. Now we said that this would bring us anything below that would be under 95%, or vice versa. Anything below this, you could expect a higher than 5% significance level. Anything above this would be less than significance level. So we have a 3.61, which means that the population, our sample, is rare. It means that we are likely to not see it, or not likely, we won't see it less than 5% of the time. So if we were to run the same survey 100 times, we would only get a sample similar to this, less than 5%, if the information was true. So what that tells us is that our null hypothesis is false. We can reject our null hypothesis. So we are going to reject null. So our population means are not equal. There is a difference between the different coffees. Now we don't know, this doesn't tell us how many of them are different. It doesn't tell us if 3 are the same and 1 is different, or if they're all different. Just that they are different quality. And this was a lot of work. If you want to take a look up ANOVA tables in Excel if you want to try this on Excel as well to do more work. But it is a very this process does tell us that these populations are different. So again, just to put in layman's term, we wanted to review coffee satisfaction. We thought that possibly coffee is coffee, it doesn't matter, we should get similar results, and that we are going to be comparing different populations. When we do an analysis variance, what we've just determined is that the coffee is different, and they are not the same. So throughout an analysis variance, we can reject our null hypothesis that our coffee population is the same, and that there are major differences within the coffee.